Hello there. Well, having gone through interpolation, it's likely that the next thing you're going to learn is about measures of central tendency and variance. So for our measures of central tendency, we have mean, median, and mode. And I trust that you're already pretty familiar with those, so I won't go any further than to give you the two formulas we use for calculating the mean. And that's because the mean is probably the most useful of those measures of central tendency when it comes to the calculations you're going to be doing in univariate statistics. And then after that, I'm going to go into the different measures of variance we have. So we have the sum of squares, the variance, and the standard deviation, and then the different formulas we use for calculating those. And then finally, we'll get into the difference between biased and unbiased formulas. So to start us out, let's take a look at our two formulas. The first one is for the population. The second one is for a sample. So when we talk about populations, often we use Greek letters to denote that we're talking about a population parameter. So for our mean, we're going to be talking with mu is equal to the sum of x divided by n. So what this is saying is that we add all our numbers up. 1, 2, 3 is equal to 6. Then we divide that number by how many variables we had, 1, 2, 3. So 6 by 3 is equal to 2. For our sample statistics, we're using x bar is equal to the sum of x divided by n. So the only difference here in how this works is that instead of our Greek letters and our capital N, we're using a Roman letter x bar and a lowercase n. Both of these typically denote that we're dealing with sample statistics instead of population parameters. However, some professors don't adhere to that and use Greek letters indiscriminately, Roman letters indiscriminately, or they use things like m to refer to the mean. But we're going to pretend that everybody follows convention and that we don't have to know that. So once we get through with our means, it's time to move on to our discussion of variance or deviation. Let's call it deviation here. Deviation is a measure of deviation from the mean or variance from the mean. And here, instead of discussing population and sample, we're going to stick to just our population formulas because we have a new category that differentiates them. We have a definitional and a computational formula. For our definitional formula, these are the formulas that are in the definition of each of these constructs. The computational formula is often a quicker, easier way to calculate. However, it doesn't show every single step, so it is not a definitional formula. There's also a chance that in using the definitional and the computational formulas, you may get a slightly different answer due to rounding errors. And you'll see that come into play in a later video where I start to go through and show you how to use all these different formulas. So the first measure of deviation we use is called the sum of squares, represented by a double S. Our definitional formula for the sum of squares is equal to the sum, that's our summation sign, the capital sigma, is x minus mu squared. So we would take each value, subtract it from the mean, square those values, and we sum them up, then we get our answer. For our computational formula, we use slightly different set of symbols. So sum of squares is equal to the sum of x squared minus n times the mean squared. These will get us to the same area with maybe a little difference due to rounding error. All right, let's go ahead and box these off with some of this so that we can tell we've moved on to the next set of formulas. Once we have our sum of squares, we can calculate our variance. Variance is our variance is seen in sigma squared, except we're using lowercase sigma instead of uppercase, like in our summation sign. The sigma squared is equal to the sum of x minus mu squared, and that whole thing is divided by n. There's another way to do this. We'll use some green to differentiate, or we could say sigma squared is equal to the sum of squares divided by n. And another way to phrase this, or another way to do this, is the mean squares. Let's go on to our computational side now. So sigma squared is equal to the sum of x squared minus mu squared, and our component over here, the sum of x squared, is divided by n before we subtract. The alternate way of doing this is if we take 1 over n, then brackets, multiply that by the sum of x squared minus the sum of x squared divided by n. We'll put that all inside the bracket. We've got room. There we go. This is perhaps my favorite formula for calculating the variance just because of how simple it is. It doesn't look simple now, but it's actually fairly easy to calculate. Now we've gone through our variance, it's time to go on to our standard deviations. Our standard deviation is represented by sigma, and as such is the square root of these formulas above. So we're going to take those same formulas. We're going to have equal to the square root of the sum of x minus mu squared over n. Or the other formula, where we have sigma, our standard deviation, is equal to the square root of the sum of squares over n, or the square root of the mean squares. This is why our standard deviation is sometimes called the root mean square. Now let's go over to our computational side. We have sigma is equal to the square root of the sum of x squared over n minus mu squared, or going back to our alternate formula, we have sigma is equal to the square root of 1 over n times the sum of x squared minus the sum of x squared over n. Now, this takes care of all the different measures of variance we have. We see that each flows from the next. So if you have your variance, you can just take that and find the square root, and you already have your standard deviation. Likewise, you have your standard deviation, you can square it to find your variance. All right. Now that we have our population parameters out of the way for terms of our variance, we're going to need a new page, and we're going to go ahead and talk about our sample statistics and the measures we use for these. Whoop, get that back under there. So, how are we going to do this? Well, we're still keeping definitional and computational. For our definitional version of the formula, we are going to use S squared to represent our variance, and we're going to use S to represent our standard deviation. Note, I am not doing our sum of squares again because that does not change. It's a universal formula, or it's a universal component rather, and we only need to make changes to our variance and to our standard deviation. So, where do we go? First, we start with the variance is equal to the sum of x minus x bar squared, and all of this is over n. So as you'll remember from when we talked about our sample right over here with our computation for the mean, we're using x bar instead of mu, and we're using a lowercase n. These both denote that we're dealing with a sample statistic instead of a population parameter. Next, we have our standard deviation of the sample is equal to the square root of the sum of x minus x bar squared, and all of that over n. We'll go ahead and mark these off, the line, and then we'll go and look at our computational side. On our computational side, we still have s squared representing our variance is equal to 1 over n times the sum of x squared minus the sum of x squared over n, and I'm out of room for my bracket. We'll pretend there's a bracket there. Then the alternate for our standard deviation is the sum s is equal to the square root of 1 over n times the sum of x squared minus the sum of x squared. Whoop. Get that outside the bracket over n, and then throw in a little bracket there. So, largely the same formula. In fact, all we've really done is replace our omega, replace sigma with s and capital N with lowercase n. If we want to go one step further, there is one other concept we need to talk about. And when we're dealing with sample statistics, we have biased and unbiased calculations. I have shown you the biased calculations. However, we have unbiased versions of these formulas. Let's take a quick look at those. So when we're taking an unbiased calculation, we step back, and instead of looking here, we go s squared is equal to the sum of x minus x bar squared over n minus 1. And that carries over for the rest of them. We have our computational formula. We have s squared is equal to 1 over n minus 1 times the sum of x squared minus the sum of x squared over n. Or down here we have s is equal to the square root of the sum of x minus x bar squared divided by n minus 1, or the computational s is equal to the square root of 1 over n minus 1 times the sum of x squared minus the sum of x squared over n. So why do we do this? Well, it's pretty simple, really. When we're dealing with the population, we don't have to do this because we're counting everybody. So everybody has a chance to vary. But when we're dealing with a sample statistic, we're only dealing with some people. And when we take a look at our deviation, so let's say we're looking at 4 numbers, 2, 6, 7, and 9. If we were trying to find our mean deviation, we'd find our mean. We'll just use a calculator for this. We save any paper space. So 2 plus 6 plus 7 plus 9 is equal to 24. Our mean for this would be 24 divided by 4 is equal to 6. So our mean, we'll call this x bar, since we're dealing with samples, is equal to 6. If we were going to calculate our mean deviation, we would look and take each of these minus the mean. So let's box that off. So we have 6. Oops, got that backwards. So we have 2 minus 6 plus 6 minus 6 plus 7 minus 6 plus 9 minus 6. And what this is equal to is -4 plus 0 plus 1 plus 3. We see that these sum to 0. So why we use n minus 1 to unbias our formulas here is because that's the number of values that are free to vary in what they're doing. Once we have these first 3 values in, we know that since the deviation from the mean is always equal to 0 when we look at all of the variables that make up our mean, because each of these is contained in the mean. And so if you find out that you sum everything together and then do this procedure and it doesn't sum to 0, you've made a mistake somewhere. So since these 3 come first, once they have their values, the final one, the 4th one in this case, has only one value it can be. It must deviate by +3, otherwise it doesn't work. And so that's why we use n minus 1, which we also call is equal to our degrees of freedom. And there you go. This has been an overview of the different formulas we use for the mean and the deviation or the variance, standard deviation in psychological statistics. We're going to go into how to use the definitional and computational formulas next. I hope this has been helpful for you. Let me know if you have any questions, and I'll post these formulas down in the description so you can look at them without having to pause the video.